load current will determine. So if you look at the ratio of the two, then those PVT effect will get cancelled out, and that's what we have done here. So your IP is nothing but VDSP over RDS, and IREF is Vsense over RDS of this, okay, and the ratio is this, okay, and RDS on of this sense is n times of RDSP. You substitute here and that's what you get. So what information you need? You need IREF. IREF is already known because it's a fixed current you are feeding here, and you need these two voltages, and you need to take the ratio of the two, okay. So which means, I mean, it's not that straightforward. You cannot divide these two voltages in analog. It's not that simple. So most of the time it's done digitally. So what you do, you take this voltage and this voltage, have an ADC. From ADC you generate these two codes and divide the code, and then multiply it by this n times and IREF. You will get the load current right away, okay. So this is a very simple method and very decent accuracy you can achieve, and most of the time you don't require, you may not need a dedicated ADC for this. You may already have a ADC in system which you can utilize if you are not looking for peak to peak. For average current, because once in a while you want to measure, okay, average current can be slower, but if you are looking cycle by cycle current, then you require dedicated ADC, okay. And you can do with a single ADC also. Let's say, if your ADC is fast enough to basically convert this analog into digital within one PWM cycle. So one PWM cycle you can measure this IREF, another PWM cycle you can measure this. So at least every alternate cycle you can get the peak current, okay. So with one ADC you can do. Same thing you can do with the NMOS if you are looking for a valley current. And once you have both peak and valley, if you add the two, you will get the exact inductor current, and you can get the average current from there as well, okay. So this is your observer based sensing. So we know that inductor is nothing but the current, inductor current is integrated version of your voltage across it. So what you do, we take the voltage and put another integrator and multiply it 1 by L, which is the gain of integrator, you can say. So you will get the same current here across. But this is only true if there is no loss in the inductor radial. The moment you have a loss, this integrator will saturate, okay. So it's very difficult actually. And another drawback of this is, this 1 by L is different than this, because this is an integrator gain and this L. So you cannot track the two. So you need to have a way to measure the inductor value and tune your gain, integrator gain accordingly. Only then you can get accuracy, and this will work under no loss conditions. So which means you can get the peak current, the ripple current, but DC current is very difficult, because your integrator will saturate. So this is another one. GMC is the same thing actually. So if you want to implement with the GMC, and we talked about this in hysteretic converter if you remember. So this will not work if you have a loss under load condition. So because your integrator will saturate. So you can get the ripple information under zero load, but the moment you apply a load, you will lose all the information, okay. So that's why I am saying here works only with the zero loss across the inductor. So you can use it for a ripple information, and you can reset the integrator every cycle so that it will not saturate. And if you remember, we did it by connecting a switch in parallel with this, and you reset every edge of the clock. So you can get the ripple information, and that is also if your gain of integrator is same as inductor, like 1 by L. So this condition you have to meet, okay. So L is nothing but C by GM. If you match this, then your ripple information you can get. So this is RC filter based sensing. Another same thing which we used in hysteretic, current mode hysteretic if you remember. But here if you see, you have both the information actually, ripple as well as the DC. So if you look at this, this is nothing but low pass filter, correct? So what is the voltage across this capacitor? So there is no loss in this resistor, which means this voltage if you integrate or pass through a low pass filter, so the DC voltage here and the DC voltage V out will give you the difference drop across RDCR. So which means if I measure the voltage across the capacitor is nothing but voltage across RDCR, and if I know RDCR, so I can take this voltage difference and divide by RDCR, I can get the DC information, and this ripple will give me the Vx will give me the, okay. So when Vx minus V out you do, you have both the components, you have a ripple, because if you measure at a Vx, it's a triangular waveform we looked at, and V out is pretty close to DC. Now if your Vx is much larger than V out, that was the condition for your current mode. Here also, like, you cannot keep Vx too small that your V out ripple will basically kill this voltage and you cannot get any information. So you want to make sure that this is large enough, okay. So this delta IL will have a K times delta Vc. K times is nothing but depending upon how you choose the RC time constant compared to this, that will give you a K factor, okay. So if this is, let's say, 100 milliamp peak to peak, you can have a gain factor here, make it 500 millivolt peak to peak. So the one difference is this current gets converted to voltage here in this RC filter, okay. So you'll have the same information. One is the voltage, DC voltage, and the ripple will be voltage, not the current, but that same inductor ripple current will get mapped into voltage here. And if you have a RC time constant same as your match with the inductor, then your voltage will be, peak to peak voltage will be same as peak to peak ripple current. So this can give you, the only problem here is this RDCR doesn't remain fixed, it can change with temperature, okay. So that's the only drawback, otherwise it's a very good technique to use a current sensing without any loss here, because you don't require any series resistor here. So you can get both ripple as well as DC information here, okay. So if you choose RF CF equal to K times L, then ripple voltage across CF provides the ripple current sensing, and K should be chosen such that RF CF is much larger than TSW, because we are looking for a triangular waveform, not exponential, okay. We don't want to have any non-linearity, because we are replicating the inductor current into the ripple voltage here. So this is sense-fed based current sensing, and this is most commonly used if you require very good efficiency and very high accuracy. So what you do actually, it's a current mirror here, sense-fed, but since this is operating in the linear, so in the current mirror actually if you have a VDS mismatch and channel length modulation is not very high, then the current is almost same. But here in the linear, even a small change in the voltage can cause a huge change in the current, okay. So which means we have to match both VGS and VDS, and that's what we do here. So we are having this if this is n times and this is 1x, so again 1:n ratio here, so which could be 1000 to 10,000 times. So and if I have, let's say, this current is nothing but this current divided by n, because if VDS is matched and VGS is matched, then the current will scale according to the W by L size of this, the ratio of this, which is n here. So this becomes IL by n, and you dump into a resistor, you get the V sense voltage. So voltage to current converter. So this voltage will contain the information of the current, okay. So how we implement it? This is how we do it. So this is VSW, this is VSW. So when this guy is on, it will have a IR drop, okay. So this will be V in minus whatever IR drop, and we want to keep this drain voltage same. So what you do, this is regulated cascode actually. So VSW, and this feedback will force this node to be same as VSW. So, now this will see the same VDS, V in minus VSW, which is seen by this guy when this FET is on. So, now you have matched both VGS and VDS. So, this will carry the same current I sense equal to IL by N. So, now you can match the current, but the problem here is like you want to do it every cycle, cycle by cycle. So, this amplifier should be very fast and gain should also be very high. If you have a very poor gain, then this voltage will not match. You will have a gain error, large gain error. So which means the both gain and bandwidth has to be very high. So, it is not very easy to implement, especially if you, let us say I am sensing I am let us say the gain bandwidth of this I have kept very high according to 50% duty cycle. Now, assume what will happen if the duty cycle goes to 10%, your current will rise much faster. So, now this guy has to track this voltage much faster. So, the bandwidth of this should be based on the maximum slope actually of the current. Okay, so another sources of error could be here, like obviously the offset, and if you have limited bandwidth, what will happen? It will not track, so that will again give you the error. Okay, so I mean I am looking here, I mean this is a ramp actually. If you look at the voltage difference, is a ramp because current is ramp, current is rising, so voltage will be ramp here. So, this has to track that ramp, and if I am not able to track properly, which means bandwidth is smaller, then I will always have some delta error, and that error will cause a difference in the current. So, accuracy will go bad.
Sir, with high duty cycle only there will be a fast shoot in current.
Why?
Like when duty cycle is 90%, then only due to high slope there will be
No.
fast.
Higher duty cycle means how your V out is high, so V in minus V out difference is smaller, so it will current rise will be slower. Okay, so another mismatch between these two FETs, that mismatch will come from layout mainly. So, most of the time we try to match these very closely, which means you have to place them very close. If you use a single device, it is very hard to match. I mean this guy is 10,000 and that guy is 1. You do not know which corner you will keep to match it. The best way you have to keep it at the center, only then you can match on an average. So, most of the time what we do, instead of a single device, we use 10 or 20 devices of this and we spread around. So, you keep at all the 4 corners in between center, on an average you can get a very good matching. Okay, so the advantage here is like everything is fully integrated, no external components is required. It's a lossless. When I say lossless, there is no additional loss in the current path, and this is very small. So, if you look comparing this is a milliamp of current compared to amp here, so it will be. So, current transformer we never use actually because it's a bulky, it cannot be built like on chip, so that's very bad. So, but this is the most commonly used in MOSFETs. Okay. Okay, so we'll look into layout techniques today. So, in order to do the layout for any analog, I mean obviously the PMIC falls into analog category. So, you should